Hey there, this is Math 6, Unit 1, Lesson 9, called Formula for the Area of a Triangle. Alright, so we began today with activity number 1 called Bases and Heights of a Triangle. And it says study the examples and non-examples of bases and heights in a triangle and answer the questions that follow. So first it says these dashed segments represent heights of a triangle. So these little dashed segments right here, and maybe I should highlight them for you right there, represents the height of this triangle, the blue triangle there. These are all heights, right there, right there. We also have a height right here, lining up to that base right there. And we have a height here, which lines up to that base. Notice that for each of these ones, they do have a perpendicular, they're perpendicular to a base. And here's our base, and here's a perpendicular line there to that base, and this base here perpendicular there. So they each represent the height, and that's how that works there. Kind of cool. These dashed segments do not represent the heights of the triangle. And so when you take a look at them, while the bases are still going to be in the same spot, here's our base, and our base, and our base, the difference is going to be when we take a look, we see this one comes down here, but as it comes down, we see that it doesn't have a right angle there. Notice these ones all have a right angle because they're perpendicular. When this one comes off the vertex and comes down here, it's close to a right angle, but again, it's not a right angle, and that's the problem with that one. This one does have a right angle, but look at where it starts. It starts here off to the side. It needs to begin at the vertex. Those are two important things there, that it has to start from the vertex, and it also has to be perpendicular. Alright? So it has to be perpendicular and come from the vertex in order for it to actually be a height there. So let's take a look then at the next question, which says select all the statements that are true about bases and heights in a triangle. So the first one, any side of a triangle can be a base. Well, that is going to be a true statement. Absolutely true. Any side can be a base. No problem with that one. There is only one possible height. Well, that's not going to be true because it depends on which one you say is the base. So for example, when we come back here, the height for this one is going to be this length because it goes from there to there. But if I was to start here, I could have another height that went from here to here, potentially, because it would go to that base, and that might be a different length depending on the shape of the triangle. Let's say I had a triangle that was something like this and like this, right? Something like that, okay? And so I might have a height from here to here, of a small little bit, but if I went from this vertex, I could have a height that went all the way down here and was a lot longer. So that's not going to be always true. A height is always one of the sides of a triangle. Well, a height is not always a side. It could be, if it's a right angle triangle like that, you could have a base and a height, but it's saying always, so we'd say no. A height that corresponds to a base must be drawn at an acute angle to the base. Again, what's the problem with that? Well, the problem with that is that we know we need to have something that's perpendicular, or at least forms a 90-degree angle. So that would be no for number 4. Number 5, a height that corresponds to a base must be drawn at a right angle to the base. That is true. That's what we just said was true when we're talking about number 4. Once we choose a base, there is only one segment that represents the corresponding height. Well, take a look up here. Here we selected the base and we had height, height, height. So there's lots of ways to have a height there. Lots of segments can be the height. You can actually have as many as you choose. So that's not going to be true. And then finally, number 7, a segment representing a height must go through a vertex. This is the key word here. Must go through a vertex. Now, we said that it should go through a vertex. That's ideal over here. So when I back up my notes, I said a vertex, but you can extend the line out someplace else. So this one here, while it's not at the vertex, it does come off of the vertex, right? And then we draw that height from there. So it does have to have some sort of relationship to the vertex, but it doesn't have to go through the vertex. So we're going to X that out. And I wish I could rewind the tape real quick because we talked about vertex being important, but it just means it needs to be as tall as that height, that vertex across from it. But because you can extend that line, you can draw that wherever you like. All right, so let's move on to this next section. All right. For each triangle, label a side that can be used as the base and a segment showing its corresponding height. Then we're going to record the measurements of the base of the height in the table. Okay, so record the measurements in the table and then find the area of the triangle. The last row, write an expression for the area of a triangle using B and H for base and height. So let's take a look at our first one. In our first example here, we see that we have a base. We can use this line right here as our base. And we can have a base of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So our base here for A, we can draw it on the chart here, as a base of 10 units. And our height is this dotted line or dashed line here, which has a height of 1, 2, 3, 4, 5, 6, 7. So this is our height. That's our base and our height, and it has a height of 7. And we'll leave that there for right now. Okay, we'll find the area in a second. Alright, over here, we could use this top part as our base, and we can use this part as our height because it has a 90-degree angle there. Our base has a length of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And our height is a height of 1, 2, 3, 4, 5, 6. And that's our height. For C, we can use this horizontal line and call that our base there. And we have a base that has a length of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And our height comes off of this vertex, but it comes down towards our base to make a 90-degree angle right there if we extend that out. And so our height is 1, 2, 3. And then finally with D here, we can call this our base, which has a base of 1, 2, 3, 4. And our height is this dashed line because it makes a 90-degree angle, which has a height of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Alright, so that's what we have to start with. Now if you recall from our last lesson, one of the things we talked about was that I can extend the triangle, I can make a copy of it to turn it into a parallelogram. Oh, this time, sorry, get back up here. It's the joy of using the dot cam sometimes, kids. Sorry about that. There's my table filled in. So if you didn't get the table notes, I already filled in the base and the height right there as well as we're going along. Sorry about that. Hope you were able to keep up. So to extend this here, I know, remember this base has a base of 10. So if I extend this line out, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to there, and then connect my line here, I can form an identical copy, or a copy of the triangle to make a parallelogram. Now with the parallelogram, we said that the area of the parallelogram is base times the height. Right? That was our formula to find the area of a parallelogram. But in our case here, because we're using the triangle, we don't need the whole thing. We only need how much of it? We only need half of it. So when I take a look at this triangle here, if I take a look at it, if I have 10 times 7, 10 times 7 is equal to 70, right? So it's equal to 70, which is great, but I only want half of it. So if I multiply it by another half, then I find that the area is actually going to be 35 square units, because I only want half of that area. For B, I have 11 times 6, which is 66, but again, I only want half of it, so we would say it's going to be 33. C, I have 10 times 3, which is equal to 30, which would be great. Again, if it was a parallelogram, that'd be fantastic, wouldn't it, right? Let's extend it out here. I can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, something like that. Extend it there, and now I have a parallelogram. So yes, that whole thing would be 30, but I only want half of it, so we're going to say the area is 15. And for the last one right here, well, it has a base of 4 and a height of 11. Again, we could extend this down, same idea, and we could do it, well, we won't do it right now, but I could say, well, that's 44, but I only want half of it, so it ends up being just 22. This happens every single time. So what we're noticing here is that I am doing a base, I'm multiplying it by a height, but I'm also multiplying it by what each time? By a half, in order to find out the area. So the way we would write that down is we would say that the area of any triangle is going to be half of the base times the height. And that becomes how we find the area of a triangle. That's our expression. 1/2 of the base times the height. Alright, let's see if we can use this now on the next page. And I'll try to keep the page visible for you. I'll zoom in there a little bit. Should be okay. Alright. For each triangle, circle a base measurement that you can use to find the area of the triangle, and then find the area of any 3 triangles. Alright, so let's look at this one here. We have a vertical line, or we have a perpendicular line here making that right angle, so we can say this would be a great base for us, no problem. On this one, I'm going to call this the base, just because this one goes up and down, and it's easier to refer to that as the height, just visually, the nice right angle there. Over here, I have, one's a little bit trickier, right? I'm going to go ahead and call this the base. And the reason I'll call that a base is because I do have this line that extends this way, making the perpendicular line there. I can call this my height. Over here, I can call this my base, and refer to this as my height. And this last one, this becomes my base, and this perpendicular line there becomes my height right there. So, in terms of finding the area, using what we know, again, using what we just did in the last lesson, 1/2 of the base times the height, on this one, I would have 1/2 times the base, which is 5, times the height, which is 6. And so it's up to you how you want to work this out. Sometimes you might want to multiply them together first and then divide by 2 or multiply by half. Sometimes you might just want to just cut an even number in half right away and multiply it a little quicker, right? So half of 6 is actually 3, and 3 times 5 is 15. If I wanted to, I could have done 5 times 6 is 30 and cut it in half to make 15. So I can say 15 centimeters squared for that one. Here, I have half of 4 times 4. Well, 4 times 4 is 16, and half of 16 is 8 centimeters squared. Here, we have 7 and 3, so we would write down 1/2 times 7 times 3. These aren't even numbers, so it's not quite as clean, but I have 21 right there, and half of 21 is going to be 10.5. For D, I have 8 times 3.5, but again, this is 1/2 of 8 times 3.5. So I would do this first. I do half of 8 is 4, so then I come over here and multiply by 4. 5 times 4 is 20, and 12, 13, 14. We have 1 digit behind a decimal, so I'll move that over 1 spot, and we have 14 as our answer. And for our last one, we have 1/2 of the base, which is 6, times the height, which is 5. And again, we have 6 times 5 is 30, and half of 30 is 15. Alright, so I did all 5 of them there just to make sure you got those, and not sure which ones you wanted to do, but that's what we did there in our class today. Alright, take a look at the summary. It says we can choose any of the 3 sides of a triangle to call the base, right? And base can be any of the 3 sides, no problem. The term base refers to both the side and its length, the measurement. A corresponding height is the length of a perpendicular segment from the base to the vertex opposite, right? The opposite vertex is the vertex that is not an endpoint of the base. So We talked about that vertex importance there, but remember the vertex doesn't have to come off the vertex, but it does need to be perpendicular. That's key. Right? Here are 3 pairs of bases and heights of the same triangle. The dashed segments in the diagrams represent heights. So here's our base, and you notice this vertex off here, we get a height off the vertex. This one we have a vertex, and we have a height off of it. And here the vertex is out here, and the height comes off of that one there. Alright, so our height and our base each time. A segment showing a height must be drawn at a right angle to the base. Very key, right angle to the base for a height. But it can be drawn in more than one place. It does not have to go through the opposite vertex as long as it connects the base in a line that is parallel to the base and goes through the opposite vertex as shown here. So again, you can have multiple spots that can be considered a height as long as whatever line it's starting from does connect to that vertex right there. Right, that's key. As long as this line's here, it's coming off of there, and you have a base that extends out, then you're good to go. So the base pairs in a triangle are closely related to those in a parallelogram. Recall that 2 copies of a triangle can be composed into 1 or more parallelograms, so we could copy it and make it there or make it like that. And each parallelogram shares at least 1 base with a triangle. For any base that they share, the corresponding height is also shared as shown by the dashed diagrams. So they have the same height no matter what. And then we can use that to recognize once again that base height measurements and our knowledge of parallelograms, we can use that to find the area of any triangle. Okay, so we knew that the parallelogram, the formula for the parallelogram area of parallelogram was base times height. And just as that's the case here, we also know the area of a triangle is 1/2 times the base times the height, because the triangle is half of a parallelogram. So we take a parallelogram and we cut it in equal parts like so, half like that. That becomes a half, and that becomes the other half, and together it makes the whole. So we use that half as part of our formula right there. All right, and that's the idea. They give you a couple of examples here to look at to kind of clarify your understanding there, and that's really about all there is. All right, so we're going to pause there and give you a moment to work on your homework, and then we'll come back and check it together. Okay, now for your homework. Math 6, Unit 1, Lesson 9. Select all drawings in which a corresponding height is given for a base B is correctly identified. Alright, so remember it has to come off of the vertex and it has to form a perpendicular line off that somehow. So here's our base, and then we look here, here's our base, and here's a height. We have a 90-degree angle. That looks like no problem. Here we have a base, and we have a height. We have that 90-degree perpendicular angle, and it looks great. Here we have a base and a height. Do they connect to make a 90-degree angle? Nope, they don't, so it's not going to work for us. Right? These ones all connected and came together to make that 90 degrees. There's 90 degrees here, sure, but it's not connecting to the base. For D, we have a base and we have a height connected to 90 degrees. That works fine. Here we have a base and we have a height. Yes, they connect, but they're not connecting at a 90-degree angle. That's not 90 degrees, is it? So it's not going to work. For F, we have a base and we have a height, and it connects at 90 degrees, so that works as well. So we would say A, B, D, and F all work great. Number 2. For each triangle, a base and its corresponding height are labeled. Find the area of each triangle. Okay. Let's take a look at the first one. We have a base of 1, 2, 3, 4. Right, so 1/2 times 4 times the height, 1, 2, 3, 4, 5, 6. And so 4 times 6 is 24, and half of 24 is 12. So we'd say this one's going to be 12. Over here we have a base of 1, 2, 3, 4, 5, 6, 7, 8. So 1/2 times 8 times our height, 1, 2, 3, 4. Alright, half of 8 is 4, and 4 times 4 is 16. Over here we have a base of 1, 2, 3, 4, 5, 6. So 1/2 times 6, and a height of 1, 2, 3, 4. So once again, we have 24 there, and half of 24 is 12. All right, so area of A is 12, B is 16, and C is 12. How is the area related to the base and its corresponding height? Well, what would we say here is, and you write in your own words, that the area is half of its base times its height. So area is half of its base times its height. All right, moving on, number 3. It says, here is a right triangle. Name a corresponding height for each base. Okay, let's take a look at this one. We're going to look for a corresponding height for each base. All right, so I'm going to use 3 colors here. Ready? Okay, so let's look at side D. So for side D, what is the height of side D? If that's side D, which line becomes the height? You would say this one right here, because it's perpendicular, 90 degree. So G works with side D. All right, how about for side E? Here is side E, right there. Which line makes a 90 degree angle with side E? We could look here, we have a line right there, makes a 90 degree perpendicular. So we would say F. And then finally, for side F, which is here, which one makes a 90 degree with that one? Well, that would actually be right here, side E. And that's how it works. So you're actually looking at how each one of the sides can become a base, and then it can have a different height. And that's what we're proving there. Okay? Number 4. Find the area of the shaded triangle and show your reasoning. All right, so let's take a look at this. We have, in this case here, we have a base which is 6. We can call that the base. This is my reasoning here. There's the vertex. Now, while I don't have a line that goes straight down from there to there, what I do have is I have this line that goes across, and it's parallel to this one, it seems to be, and it comes down, and I can call this like a height from this spot. Well, if that's a height right there, then I have the number I'm looking for. That's my height. So I really have 1/2 times the base times the height. And so half of 6 is 3, and 3 times 6 is 18. Is there another way of doing that? Sure, there certainly could be. I could recognize that I have 2 triangles here, and I have a giant square. The giant square is 36, right? So let's say you did the 30 this way. That's one way. 36 is a square. And now I'm going to subtract that triangle and subtract that triangle. This triangle has an area of 1/2 of the base times the height. 1/2 of 6 times 4. This is 24, and that becomes 12. This triangle has 1/2 of the base, which I could say is again a 6, and a height of 2. 6 times 2 is 12, and half of that becomes 6. 12 plus 6 is 18. So if I took the area of the square and I subtract those 2 triangles, the 12 and the 16, what am I left with? I'm left with 18. So there's a couple ways you can do that. It's definitely easy to recognize that this height right there is the same one right there. But it depends on what you saw. Number 5. Andre drew a line connecting 2 opposite corners of a parallelogram, like so. Select all true statements about the triangles he created by the line and Andre drew. All right. Each triangle has 2 sides that are 3 units long. Well, here's a 3 unit long one and a 3 unit long one. Does each triangle have 2 sides? Well, that's a longer than 3, 3. So we would say no, they only have 1 side. 1 side only. And B. Each triangle has a side that is the same length as the diagonal line. Well, there's the diagonal line, right? So does every triangle have that same length? Yep, it sure does. They share a common side. Each triangle has one side that's 3 units long. That is true. There's this one and this one. When one triangle is placed on top of the other and their sides are aligned, we will see that one triangle is larger than the other. Well, we know that's not true because this is going to be cut in half. It's going to be a copy of it, right? So let's just show you real quick. If I took that and I put it right on top of the other one, it's not larger, it's exactly the same. That's the way that works when you cut a parallelogram from vertex to vertex. So that's not true. The two triangles have the same area as each other, yes, and we just saw that. Finally, number 6, it says here is an octagon. On the page, here's an octagon. While estimating the area of the octagon, Lynn reasoned that it must be less than 100 square inches. Do you agree? I explain your reasoning. So just an estimating, she says less than 100. Well, what do we know? We know that the distance from here to here to here, if we draw a little square around the whole thing, this distance, 3 plus 4 plus 3 is 10. This distance, 3 plus 4 plus 3 is 10. So if it was the square, the area of the whole square is 10 by 10, and 10 times 10 equals 100, and we know we're going to be subtracting 4 triangles, right? So since we're subtracting 4 triangles, of course it's going to be less than 100, so I would say we definitely want to agree with that. Now to find the exact area, we know we're going to take the area of the square and we're going to subtract from it the 4 triangles. That's our goal here. This isn't a real equation. This is me saying 100 minus 4 triangles. So triangle 1, we have a 3 and 3, so we have a base and a height, right? So 1/2 times 3 times 3. Well, 3 times 3 is 9, right? 3 times 3 is 9. And so I have 9 times a half, so I get 9 over 2, right? If I do not a half times 9, I end up with 9 over 2. And that's not a very pretty number to look at, but again, I'm not done yet. How many of these do I have? I have 4 of them. So let's multiply this by 4. Alright, so 9 times 4 is 36, and 2 times 1 is 2, and 36 divided by 2 is 18. Alright, so now we're talking 18 is what? The area of these 4 triangles. 1, 2, 3, and 4. So if we do 100 minus 18, that will give us the area of what? The area of the octagon, which would be 82 inches squared. Alright, that's it for today. Have a great one, and we'll see you next time.